So what we're going to do here is approximate an integral using the midpoint rule this time. And so if the purpose is to approximate an integral, then it's usually better to choose xi to be the midpoint. And this is something we discussed last week, that usually the midpoint is going to give you a more realistic answer, and an answer that's closer to the actual value of the integral than using the left end or the right end of the intervals. So we often denote this with an x bar over the top, just to say that that's the midpoint. It's just some notation that you might see. So we would say that the integral of f of x with respect to x from a to b is approximately the sum of all of these rectangles with a base of delta x and a height of f of x bar being the midpoint of each interval from 1 to n, however many rectangles you're adding together, and we could rewrite that like this, right? They all have a delta x. We factor that out. We're left with just the heights of each of the rectangles. So in that case, delta x is b minus a over n, just like it always has been. But we want to consider now that xi bar, which is the midpoint of each of those intervals, is going to be represented as xi minus 1, which is the left side of each rectangle, plus the right side of each rectangle, but it's half of that because it's the midpoint, right? It's right in the middle of the left and right side of each rectangle that we're going to add together. So that's going to give you the location of xi, and that's essentially the midpoint of xi minus 1 and xi. So that gives you the very middle of the rectangle, and so we can evaluate f of that point to give us an approximation of the height of that rectangle. So what we're going to do is use that midpoint rule, and we're going to assume that we have 5 rectangles to approximate the following integral. And so let's write down some of the things that we've been given. We know that the function is 1 over x. It looks like a is 1, b is 2, and n is 5. All of that is useful information. We can calculate delta x here, and that's just going to be b minus a over n, which in this case is 2 minus 1 over 5, which is 1/5. So now we know that the width of each rectangle is 1/5. So let's consider what these intervals are going to be then. We're going to have our initial, or left-hand side of this whole interval. We say that that is our x naught, or a. That's 1. But where is x1? Well, it's going to be 1/5 greater than that. So x1 is going to be 6/5, right? 5/5 plus 1/5. And then we're going to have our second point on our interval is going to be 7/5. And we've got 8/5. That is an 8. We've got 9/5. And of course our final right end point of this interval is 10/5, which is 2. And so this tells us on our x-axis, and I could just sketch a little picture here, which I guess I'll do. If I've got 1 over x is my function, and we know that that looks like this. And I'm evaluating this thing from 1 to 2. So it's just this interval that we're looking at. We've just sliced that interval up into 1, 2, 3, 4, 5 chunks, all of equal length, and that equal length is 1/5. So that's the base of each of these rectangles. And now what we're going to attempt to do is find the midpoints of each of those mini intervals, and we're going to use those to evaluate the function. So what we're going to say here is that this integral from 1 to 2 of f of x, or in this case 1 over x, is the same as, or is approximately the same as, it's probably more proper to write an approximation here, from 1 to 5 of f of xi bar times delta x, and we know some of these values, and let's just look at notation-wise what this is going to end up being. Remember, I can pull that delta x out because it's going to be included in each one of these values that we're going to be adding together. But that's going to be times I'm going to have f of, what will be the first one of these values? Well, it's going to be the midpoint of these two numbers. So I need to find the middle of 1 and 6/5. So I'm going to use that little formula and actually calculate where that midpoint is going to be. It might be useful to think of 1 as 5/5 here. So that's going to be 11/5 divided by 2, which is 11/10. So that's my first value that I'm going to plug into my function, f of 11/10, because I'm using my midpoint rule here. I need to do the same thing with x1 and x2, with x2 and x3, x3 and 4, and x4 and 5 to get those values. So I've just gone ahead and plugged those in. That's what each of these values are going to end up being. You'll have 11/10, 13/10. Now these are the midpoints of each of these intervals. It's right in the center of each one of these. So our rectangle's heights are going to be determined by the middle of each of these intervals. And I'll plug those in. Now just consider what's going to happen here. If I plug 11/10 into this function, that's 1 divided by 11/10, which is the same as 10/11. So this is a pretty easy calculation to make, and I'll just write out our next step here. It's going to be delta x, and we calculated delta x to be 1/5 times 10/11 plus 10/13 plus 10/15 plus 10/17 plus 10/19. And now I should use a calculator to evaluate that. And I'm going to get 0.691908. So that's approximately that value under the curve, or the area under the curve there, of that function between 1 and 2 using our midpoint rule. So let's look at some of these properties of these integrals that we're going to begin to use to save us some time. So we defined this expression to represent the integral from a to b of a function f of x. And when we do this, we assume that a is less than b. So notice, if we were to reverse a and b, then the formula for delta x would change, because normally we write it as b minus a over n, but then it would become a minus b over n. And so if I wanted to represent this in the way that I normally do, I would reverse these, but I'd have to pull a negative out. And so one thing that you would notice happening here is that if we reverse the order there, and we say that the integral is from b to a of f of x dx, that's the same thing as from a to b of f of x dx, except the whole thing is negative. So we can use this, but we have to know that once we switch that order of our endpoints, we've created a negative integral rather than the positive version of the integral. Also, if it turns out that a equals b, then the change in x is obviously 0. So if you were to calculate this from a to b of a function, then that's essentially the same thing as saying from a to a if they're the same. And that's just nothing, because you're not spanning any distance on the x-axis, so there would be no area under that curve. All right, some other basic properties that I want to go over here before we're done today. If you have a constant function, which we usually call c, then you take the integral of that function from a to b. Turns out that that's going to be exactly the same thing as just multiplying that constant value by the difference between a and b. Also, one property that makes a lot of sense, and we've seen examples that are similar to this with our summations and with our limits and things like that, but if I'm taking the sum of two functions and taking the integral of that sum, that's the same as taking the integral of each function over that same interval and then taking the sum. This also applies to differences. It's the same exact concept when we're subtracting. The reason this is written as 2 and 4 is in your book it lists these as the second and fourth integral properties, but there is a third property that they put in the middle there. And it's another extension of a property that we've seen many times this year. Essentially, if I'm taking the integral of a function that is being multiplied by a constant, I can remove that constant from the interval and then multiply the result of that integral by that constant after the fact. So these properties should be pretty similar to some properties that we've seen with other types of functions throughout our calculus units, but we are going to start applying these later on down the road.